Welcome to Aribindi Academy's Micronutrient 101 series. Today, we'll be talking about anemia and vitamin B12. When we think of anemia, we think of iron deficiencies. But what about vitamin B12? Vitamin B12 is a very important micronutrient, and deficiencies can lead to a type of anemia called megaloblastic anemia. Red blood cells have a high cell division rate, and this type of anemia occurs when red blood cell replication is impeded. Because of this, these cells will be bigger than normal and smaller in count, leading to symptoms like fatigue, weakness, and shortness of breath. Why is this? Vitamin B12 contributes to processes involved in cell division and DNA replication, like chromatin remodeling, gene transcription, and nucleotide synthesis. So vitamin B12 deficiencies can lead to problems with cell division. Let's look into this mechanism. Vitamin B12 is a cofactor for an enzyme called methionine synthase, or MTR. 5-methyl-THF transfers its methyl group to vitamin B12, which then transfers that methyl group to homocysteine, which turns into methionine. Methionine then reacts with an ATP molecule and becomes S-adenosylmethionine, or SAM, the universal methyl donor, essential for DNA methylation reactions. These methylation reactions are also important for hundreds of reactions, including the regulation of genes. Vitamin B12 is also very important for nucleotide synthesis. After giving its methyl group to vitamin B12, 5-methyl-THF is converted to THF. THF can then be converted to 10-formyl-THF by the enzyme MTHFD1. 10-formyl-THF can then be converted into nucleotides, specifically purines such as adenine and guanine. And from 5,10-methylene-THF, also synthesized by MTHFD1, we can get thymidine, which is also the rate-limiting nucleotide for DNA synthesis. So without B12, MTR can't work. You will have no conversion to THF, leading to accumulating 5-methyl-THF, also known as the methyl trap, because the methyl group is now stuck there and can't transfer to B12, impairing nucleotide synthesis and DNA replication. You will also have no homocysteine to methionine conversion, and therefore no S-adenosylmethionine, or SAM, leading to reduced methylation reactions. This negatively affects how genes are regulated and hundreds of other processes within the cell. We can see, therefore, that vitamin B12 plays an essential role in DNA replication, and deficiencies can deter cell division, which impacts cells like red blood cells that divide very frequently. And this is a primary reason behind megaloblastic anemia. Why is this important, though? Well, in developing and third world countries, micronutrient deficiencies, including vitamin B12 deficiencies, are very common, especially in women and their children. In fact, a randomized control trial in India found that 51% of pregnant women enrolled were vitamin B12 deficient, making them at risk for anemia. And anemia during pregnancy can lead to growth and development defects within the baby. Some of these defects include neural tube defects, or NTDs, where there are abnormalities in the baby's spinal cord development. The child can also have or be susceptible to anemia and stunted growth and development. So back to the original question. Vitamin B12 may not be as famous as iron when thinking about anemia, but it is just as important in terms of the disease. This is especially true in populations more at risk for anemia, such as women of reproductive age and infants. Thank you for watching, and I hope you've learned a little bit more about vitamin B12 and its importance in terms of nutrition.
Created using Powtoon.